Today's video is going to be about the chi-square distribution and several different versions of chi-square tests. Before we get started, let's do a very quick review of what a chi-square distribution actually is. And here are the most common distributions used in hypothesis testing. The normal, which you get a normal distribution if you add up a lot of random numbers. You get a chi-squared distribution if you add up a lot of independently generated squared normally distributed numbers. So to make this simple and straightforward, a chi-squared distribution, the reason why it's named a chi-squared distribution is it involves adding up squared things. And so the technical definition is you're starting with z distributed objects. You're starting with things that have a standard normal distribution, and then if you add up some of those standard normal things squared, that gives you a chi-squared distribution. And if what you're adding up really are standard normal distributed objects, then how many you add up, n of them, is going to be the degrees of freedom. However, in practice, the degrees of freedom, even though it's going to be related to how many things you're adding up, normally it's going to be slightly different. And so that's the tricky part with a chi-squared distribution. You're adding up squared things, that's kind of easy, but the degrees of freedom can be somewhat tricky. Let's go through some particular examples of chi-squared tests so you can see how this works. The first chi-squared test most people learn is a chi-squared test where you have one sample of data and you calculate a sample variance. And what you want to do is compare that to some null hypothesis value for the variance. So your null hypothesis says the variance is equal to a number. You want to test from your sample data how likely is it that this sample came from a world where the population variance really is whatever the number is. And so you calculate your sample variance. Here's the formula for your sample variance. Why am I making a particular point of looking at this? Well, look at the top of the sample variance formula here. It's the sum of xi, some numbers, your data, minus x bar, squared. That's why we're looking at a chi-squared in this case, because it's the sum of things squared, which is exactly what a chi-squared distribution is all about, the sum of things squared. And to get the variance, the sample variance, you divide it by n minus 1. So if you're doing a hypothesis test, is this sample variance equal to some number, the chi-squared statistic you're going to calculate on the top is n minus 1 times the sample variance. Well, what is n minus 1 times the sample variance? All we're doing is multiplying this variance by n minus 1 to cancel the n minus 1 on the bottom, and you're left with the numerator, the sum of each number minus the mean squared. And so you can rewrite, I like this way because it's easy to see why this is a chi-square distribution. It's the sum of the deviations squared on the top, and then on the bottom you put the null hypothesis value for the variance that you think it should be. So for example, suppose you were always told that the standard deviation of IQ is 15, and that's true for the entire population in general. Suppose you wanted to check to see if that's true for Harvard University students. You take a sample of 23 randomly selected Harvard University students, and you find that the IQ standard deviation from your sample is 9. Now, the test is about variances, so what we have to do is square these standard deviations to get the variances. And so the null hypothesis we're talking about is, should we assume that the standard deviation is 15, or 15 squared is 225. So the null hypothesis value is that the variance equals 225, 15 squared. And the alternate hypothesis would be that the variance is not equal to 225. It's something different, right? So the alternate is that the variance of the population of Harvard students is not equal to 225. So how are we going to test this? Well, let's suppose we want to use an alpha of 0.1 just for fun. So alpha equals 0.1. This is a two-tailed test that we're using here because we have equal and not equal in the alternate hypothesis. And so with an alpha of 0.1, we're going to divide that alpha into two tails, right? So we're going to have 0.05 in the left tail, and we're going to have 0.05 in the right tail. So if we want to look up our chi-squared critical values, here, let's go get a table here. Remember, we're going to have 0.05 in each tail. Okay, I Googled chi-square distribution, and one of the links was for this site at the National Institute of Standards and Technology, NIST.gov, and some of the chi-square distribution tables I found weren't complete enough. They only had values for the right tail, and some people only focus on the right tail. But for what we're doing right here, we need tables that deal with the left and the right tail. Now, why is that? Well, here is a drawing of the chi-square distribution. As you will notice, it is skewed to the right. It is not symmetric. Because when you're adding up squared numbers, you cannot get an answer that's less than 0. And so the answer for a chi-squared statistic has to be positive. And most of the probability is clumped toward the small numbers of degrees of freedom here, and it is skewed right. However, with very high degrees of freedom, it does start to get more symmetric as you get this distribution away from a clump around 0. We need to look up two critical values. Notice, not like the t or a z distribution, these two values are not going to be the same with one negative and one positive because you can't have a negative value for chi-squared. So we're going to have to look up one value for chi-squared that leaves 0.05 in the left tail. On this graph, they have written 0.025 for an alpha of 0.05, but we're going to want one with 0.05 in the left tail and 0.05 in the right tail. So I'm going to click this link here for lower critical values for our left critical value here. Now, before we can look at this table, we have to know how many degrees of freedom are we going to use. Now, I forgot to talk about this. With this particular test, the degrees of freedom are n-1, and the n-1 degrees of freedom comes from the denominator in the variance here that you're using. So n-1 degrees of freedom, I said I had a sample of 23 Harvard students. So let's go back to this table here. And 23 Harvard students minus 1, 22 degrees of freedom. So we look at the row with 22 degrees of freedom, and the column 0.95 will leave 0.05 in the left tail, because this tells us the probability of exceeding the critical value is 95%, 0.05 less. So this is going to be our critical value right here, 12.338. So let me write that down. And now let's go back, and on this page they have the critical values for the upper end of the distribution. And what we want is 0.05 in the right side, again 22 degrees of freedom, and it's going to be this one, 33.924. So 33.924 is going to be the upper value. So let's go back and actually calculate our statistic. So this one is pretty simple to calculate. We need to take n minus 1 times the sample variance. Okay, our sample standard deviation was 9. Our sample variance will be 81. And so we take n minus 1, 22, times 9 squared, or 81. That's going to give us the numerator of this chi-squared statistic. Then we need to divide that by the null hypothesis value of the variance, which is 225. So 225 on the bottom. So pause the video and calculate that and see what you get. So the chi-square statistic we get here is 7.92, and that 7.92 is outside of the range. It's lower than this lower critical value. So an alpha of 0.1 means that if the null hypothesis is true, 90% of the time we should have samples that generate chi-squared statistics between these two numbers, 12 and 34 roughly. And ours is not in that 90% interval, it's outside of it. And so this 7.92 is lower than this lower chi-square critical value, and so our decision would be to reject the null hypothesis. And so we have enough evidence based on this sample of 23 Harvard students. The standard deviation of the sample is low enough and the sample size is high enough to give us a chi-square statistic where we would reject the null hypothesis. The variance is not equal to 225 for Harvard students. It's something lower. Well, one last thing before I move on from this example. If you wanted to calculate a p-value for a chi-square distribution, since that's a little different, let me run through that really quickly. Our chi-square statistic with 22 degrees of freedom was 7.92, and let's take that over to Excel and show you what that will look like. Now, keep in mind that here, when you think about the chi-square distribution and that shape that is not symmetric, let me bring that up again. So here's this general skewed shape of a chi-square distribution, that the mean, the number that's roughly in the middle, now this is not exactly the number in the middle, but to get an idea of a number that would roughly be around the middle or the median of this distribution, is the degrees of freedom. And so looking at this particular graph on this website, I would guess that the degrees of freedom is somewhere around 2 or 3 or maybe 4 for this particular distribution. And it's the number where it's about divides 50% of the probability on the left and about 50% on the right. Now, why is that important? Well, let's go back and look at our two critical values. The number on the right is our upper critical value, and the number on the left is the lower critical value, where between these two values are about 90% if our alpha was 0.01. The number roughly in the middle between these two is about our degrees of freedom, 22. Now, why that's important is when you go and look up p-values, you need to have a picture of this distribution in your mind with, say, 22 in the middle, 33 on the right, 12 on the left, and this number 7.92 is going to be very far on the left side, with most of the probability above it and a small amount below it. So let's take that 7.92 over to Excel to calculate the p-value. The formula we want to use is equals chi dist, and Excel tells us it wants an x value and a degrees of freedom. And the x was 7.92, comma, and 22 degrees of freedom. what does it tell us here? 0.9973. If you have a picture of this distribution in your mind, that this 7.92 is very far on the left, then you immediately will be able to tell what Excel's giving us here. It's giving us that 0.997 is the probability of being to the right of 7.92. And so what we really want to calculate a p-value is the probability of being less than that. So let's say equals 1 minus this 0.997, and we get a very small probability, 0.026343. This is the area less than our statistic in one tail. Since this is a two-tailed test that we were doing, this is half of the p-value, and we need to multiply that by 2 to get the entire p-value. So equals 2 times. So our p-value is about 0.005 in this example. So let's move on to our next example of a chi-square goodness of fit test, where we're taking the sum of squared things, the sum of squared deviations, and look at a goodness of fit or independence test. So I consider these two tests to be basically the same thing. The devil's in the details. There are some differences here between the two. Our chi-squared statistic for a goodness of fit test is based around the idea in the numerator you have your observed data from your sample, and you want to see how far that observed data is away from what a null hypothesis would expect. And you're going to calculate that difference, that deviation, and square them and add them up. So that's the numerator, the sum of squared differences. And then on the numerator is the expected value. So you want to do these one at a time. I should probably have the sum outside of this fraction, actually. So I have some bad notation here. So you take the observed minus the expected squared, divide it by the expected, and then you add those things up. So I should have written this differently. The tricky part with a chi-squared test is something that is difficult for me to memorize for all the different kinds of chi-squared tests that are out there when you're talking about a goodness of fit or an independence test, is what are the degrees of freedom? I'll just give you the degrees of freedom for a couple of different kinds of tests, and I'll mention some ways to think about why it is. So let's go with a chi-squared independence test. Now, the idea of statistical independence is that knowing a characteristic of something or someone does not change the probability that something else happens. So let me say that again. In formal statistical language, we say that the probability of A given B is the same as the probability of A. In other words, knowing something B doesn't change the probability that A happens. Now we're going to test this. Are two things independent? Does knowing one thing change the probability of something else? Now, there are some formulas for doing this. I don't like formulas. I like understanding what I'm doing. So I'm going to show you what's going on, and you can look at the formulas in textbooks or on other websites and think about how to do that, but I want you to understand what it is we're doing and what it is we're calculating. And this will become useful because it applies to many different cases with these goodness of fit or independence tests. Here is some actual data from a paper by Michael Radelet. I believe it was in 1981, where he was studying death penalty cases in Florida for murder. And kind of summarizing some of the data he was looking at, here are white defendants on the top row, black defendants on the bottom row. And we look at whether the white and black defendants received the death penalty or not for being accused of a murder. And if we're testing the null hypothesis that race is independent of whether you get the death penalty, what we're saying is we think, or the null hypothesis is at least, that race doesn't matter in determining the probability that you get the death penalty. So that's what we're testing here. The probability of getting the death penalty is equal for whites and black defendants. That's basically what the null hypothesis is saying. So how are we going to do this? Well, we have our table of actual data, and these 4 cells here in the middle are the important ones. And we want to make another table down here. Fill in these yellow blocks for what would we expect these numbers to be if the null hypothesis was true, if the probability of getting the death penalty really was equal for everyone. So here's the basic idea. If it was equal, if the probability of getting the death penalty were equal for everyone, what would that probability be? Well, our observed probability for everyone, regardless of race, of getting the death penalty is equal to 36 people in the entire sample out of 326 total got the death penalty. So our observed probability, or proportion, is 36 divided by 326. And that equals about 0.11, 11%, and some change. So normally I wouldn't round off this much, but we'll call it 11% to make it easy to talk about what's going on. So how are we going to fill in this expected table here if the null hypothesis was true? Well, if the null hypothesis was true and the rate is same for everyone, then 11% of these white defendants should be getting the death penalty, 89% shouldn't, and 11% of these black defendants should be getting the death penalty, and 89% should not. So all we have to do is calculate those numbers. What is 11% of 160? Well, 0.11 times 160 equals 17.6. So we put that in the table here. And we can just subtract. Once we know this one number, let's just be clear about this. I want you to see this next step. Once we know this one number, we can fill in the rest of the table without any multiplication or complicated values at all. Because knowing the one bit of information right here, we know that 17.6 plus this value has to equal 160. So 160 minus 17.6, well, that's going to give us something like 142.4. Yeah. Now, also these numbers have to add downward here, that 17.6 plus something will have to equal 36. And so what do you add to 17.6 to get 36? So it's not a real complicated calculation, but I want you to see that that one number determines all the other numbers in the table and what they will be. This is an important idea that we'll come back to in just a second. So 36 minus 17.6 equals 18.4. We'll go there. And here, 18.4 plus something equals 166. So 166 minus 18.4 equals 147.6. All right. So now we have our what would be expected if the null hypothesis is true. What would the data look like? Well, we would expect about 18.4 of the 166 black defendants to get the death penalty. Now let's just verify that that's 11% the way we did it, right? So 0.11 times the 166 black defendants should give us that 18.4. And Actually, we get a number more like 18.2 something, and that's because, see, I made this mistake. I rounded that 11% a little too much. Let's ignore that for the moment, but I want you to remember that you really shouldn't be rounding these probabilities that much, because they do add to cumulative errors as we go along. But let's assume this table is pretty darn close to being correct. What do we do now? Let's go back to this formula up here. Chi-squared statistic is going to be the observed minus the expected squared divided by the expected. And then you add all those things up. So what we do is we look at these four numbers and compare them to these four numbers. Observed in the top, expected on the bottom. And you just calculate that chi-square statistic. So you pause the video and calculate this, and I'll do the same. So going through these calculations, 19 here, observed, minus 17.6 expected, squared, divided by the expected, plus, and doing that for each of the four cells, get an answer of 0.245. That's our chi-squared statistic. Now what we need to do is figure out what our chi-squared critical is, or criticals are. Now in this case, this chi-squared test, goodness of fit, or independence tests are always one-tailed tests. Now why? Let's just look at the formula to see why it has to be a one-tailed test. Always look at a formula to see what would this chi-squared statistic be if the null hypothesis was true. What if these observed values were exactly equal to what the expected values are when the null hypothesis is true? Now this is actually impossible for this to happen because our observed values have to be integers and our expected values are not integers. And there are some formulas people use to correct for the fact that this is not an integer, but we're not going to worry about that right now. But what if the observed and the expected were all equal? Well, this would be 0 squared. Divided by whatever's on the bottom doesn't matter. You're adding up a lot of zeros. Under the null hypothesis, the chi-squared statistic is 0 if it's perfectly true. You're only going to reject the null hypothesis if the chi-squared statistic is large, meaning there are large differences between the observed and the expected. So that makes this a one-tailed test. So let's go look at our chi-squared table and see what a chi-squared critical would be. But before we can do that, you have to know how many degrees of freedom are there in this test. For a chi-squared test of independence, where you have a table with rows and columns, the degrees of freedom is calculated by number of rows minus 1 times the number of columns minus 1. In this case, since we have 2 rows and 2 columns, this ends up just being 1 times 1 equals 1 degree of freedom. Now why is that? The intuition I can give you is, remember when we were calculating this table, and I said that every number in the yellow here can be calculated from just knowing one of the numbers. That's actually what we did. That's a little bit of intuition to see why it is we only have 1 degree of information, 1 degree of freedom, and degrees of freedom is always related to how much information is contained in the test. We only really have 1 unique number here, and all the rest are determined by knowing that one number. And so we have 1 degree of freedom. That's just kind of a way to think about why it's 1. But again, in this case, you have to really know this formula. Rows minus 1 times columns minus 1. So let's go find our chi-squared table and see what the chi-squared critical would be. So here's our picture of a generic looking skewed chi-squared distribution again. And we're going to want to look at upper critical values of the distribution. And we're just going to be looking at this first row here because we have 1 degree of freedom. And if we were doing a hypothesis test, say with alpha equals 0.05, all that 0.05 would go in one tail now for a one-tailed test, and we would use a critical value of 3.841. So going back to our calculations here, if the critical value of chi-square is equal to 3 point something, I've already forgotten what it was, 3.841, it doesn't matter, it's 3 something, then this chi-squared statistic is much closer to 0, which it would be under the null hypothesis, than it is to this critical value. In fact, it would have to be higher than 3.841, this chi-squared statistic, in order to reject the null hypothesis. So what's our conclusion? Well, our conclusion is that based on this information, the probability of getting the death penalty between black and white defendants is not dependent on race. And looking at the data, this should make some sense because we have almost an equal number of whites and black defendants in the data, and almost an equal number of them getting the death penalty. So this data, on the face of it, should not be providing to us compelling evidence that there's a disparity in the application of the death penalty. And that's what the test tells us. All right, here's one last common application of a chi-squared test called a goodness of fit test. Suppose you have some sort of expectation about the distribution of categories that things should be in. And this can also be extended to test whether data fit a normal distribution or a Poisson distribution or anything. Basically what we're doing here is looking at uniform distribution in a way, but we're doing it with categorical data. Sometimes people call this a goodness of fit for multinomial data, multinomial population. So here's a little setup. Suppose a dean of a business school, not my dean, I'm not talking about my dean. Suppose a dean said, we have designed our departments so that each has the same number of majors because we want to have equal representation or something. You know, I don't know if this makes sense or not, but suppose a dean said this, and we wanted to test to see if this was true using a sample of data. So suppose there are 4 departments that are supposed to have equal numbers of majors: accounting, economics and finance, management, and marketing. The null hypothesis, assuming the dean's statement is right, then if each department is designed to where we want them to have equal numbers of majors, you could either say a null hypothesis this way, that N1 equals N2, etc., or you could say that the proportion of students in each major is all equal. And since there are 4 departments, that would be 25% in each department. So suppose we go out and calculate a sample of 45 different majors, and we find in our sample 10 are accounting, 7 are economics, 18 are management, and 10 are marketing. How could we do a chi-squared test to see whether our data fit our preconceived notion, fit that all were equal? Now, just a note here, we could just as easily have a null hypothesis saying that P1 is 10%, P2 is 30%, P3 is 40%, and P, etc. As long as those probabilities or proportions add up to 1 or 100%, this null hypothesis, they don't all have to be equal. I'm just doing that for simplicity. So if they were equal or not, how are we going to calculate a goodness of fit test with a chi-squared distribution? Well, it's the same basic idea we had back here. Let me copy this and paste it down here so we can keep our eyes on this formula. Chi-square statistic is going to be take the observed minus the expected according to the null hypothesis, divided by the expected, and then add all those up. So observed minus expected squared divided by expected, and add them all up. So what are we going to do? Well, we actually had 10 observed accounting majors in our data versus how many expected out of 45? Well, it should be 25% if they're all equal. So take our 0.25 times 45, and you get 11.25 is what we would expect there. So 11.25 expected. We had 7 econ. How many would be expected if they're all 0.25 in proportion? Well, 11.25. Same thing for management. Again, these don't have to be the same. You could change that distribution up, and you would calculate a different proportion expected of the 45. But we're just dividing it into 4 groups here, since that's what the null hypothesis says. And we're just going to go through the steps here and calculate how many observed minus how many expected. And so I'm going to pause the video. You do the calculation, and I'll do the same. Okay, so when I calculate all these observed minus expected squared divided by expected, I get 5.356 as our chi-squared statistic. Now we need to find what a chi-squared critical value might be. Now again, this is going to be a one-tailed test. Let's assume alpha equals 0.05. Before we go to the table, we have to know how many degrees of freedom do we use in a situation like this. The general rule is that it's going to be how many categories do you have minus 1. So it's number of categories minus 1 for this multinomial. We usually say it's k is the number of categories minus 1 degrees of freedom. So in this case, that's going to be equal to 3. We have 4 majors, 4 categories, minus 1. And so let's go to our chi-squared table and see what we should use. 3 degrees of freedom, again assuming alpha is 0.05 in this one-tailed test. 7.815 is the chi-square critical value. 7.815. And since our chi-square statistic is closer to 0, less than this critical value, 7.815, we would not reject the null hypothesis for this chi-squared goodness of fit test.